In this video, we get to the heart of stoichiometry by looking at how we calculate the mass of products from a given mass of reactants. Previously, we showed how to calculate the moles of product that would be formed from a given number of moles of reactant by considering this scenario here, where we were given the starting moles of butane, C4H10, as 0.85 moles, and we needed to find the number of moles of carbon dioxide that would be produced. And we use this diagram here to help, which shows that if we are given the moles of one substance and asked to find the moles of another substance, we use the ratio of the relevant stoichiometric coefficients to do the calculation. And so in this scenario, the moles of carbon dioxide produced is expressed as 8 divided by 2 times the starting moles of butane. The 8 comes from the stoichiometric coefficient of carbon dioxide, the substance we are trying to find information about, divided by the stoichiometric coefficient of the substance we've been given information about, in this case, the 2 of butane. And we multiply that ratio by the starting moles of the given substance, so that's 8 on 2 times the moles of butane, which is 8 on 2 times 0.85 moles, which gives us an answer of 3.4 moles of carbon dioxide would be produced from 0.85 moles of butane. The problem is, we never weigh out moles in a laboratory. We typically weigh out mass quantities. So, what about mass quantities? What if I were given a mass quantity of butane of 5.78 grams and asked to find how many grams or what mass of carbon dioxide would be produced? Can I start with the mass of butane and go directly to the mass of carbon dioxide? The answer is no. We cannot do that calculation directly in a one-step process like we've just seen. What we first have to do is, if we are given the mass of one substance, substance A, which could, for example, be a reactant, and we are asked to find the mass of another substance, substance B, which could be a product, we first have to go through this step of converting the mass quantity into moles using our molar mass equation, moles equals mass divided by molar mass. And that would be step 1. Once we have the moles of substance A, we need to progress to step 2, where we use the ratio of the stoichiometric coefficients, the exercise we've just been through, to get the moles of substance B. Once we have the moles of substance B, we can then use step 3 to calculate the mass of substance B by using the rearranged molar mass equation, where mass is the subject of the equation, mass equals moles times molar mass. So in this scenario, we can't do this calculation directly in one step. We have to go through a 3-step process where we convert the mass of butane to the moles of butane in step 1. Then in step 2, we convert the moles of butane to moles of carbon dioxide using the ratio of the stoichiometric coefficients. And then in step 3, we find the mass of carbon dioxide using the rearranged molar mass equation. So let's go ahead with step 1, calculating the moles of butane in 5.78 grams. Using the molar mass equation, we get moles of butane equals the mass of butane divided by the molar mass of butane, which is equal to 5.78 grams, that's the information we've been given, divided by the molar mass of butane. Now we can quickly calculate the molar mass of butane, C4H10, from the information in the periodic table about the molar mass of hydrogen and the molar mass of carbon, which have molar masses of approximately 1.008 and 12.01 grams per mole respectively. The molar mass of butane is calculated by taking 4 times the molar mass of carbon plus 10 times the molar mass of hydrogen, which gives us 58.122 grams per mole as the molar mass for butane. And we can substitute that value into the molar mass equation here to give a total of 0.0994 moles of butane. In step 2, we now calculate the moles of carbon dioxide that will be produced by using this expression. Moles of carbon dioxide equals 8 on 2 times the starting moles of butane that we just calculated. The 8 comes from the stoichiometric coefficient of the substance we're trying to find information about, divided by 2, the stoichiometric coefficient of the substance we've been given information about. That will equal 8 on 2 times the 0.994 moles that we just calculated in step 1, which gives us 0.398 moles of carbon dioxide produced. In step 3, we now convert moles of carbon dioxide into mass of carbon dioxide using the rearranged version of the molar mass equation with mass as the subject of the equation. And so we have mass of carbon dioxide equals moles of carbon dioxide times the molar mass of carbon dioxide. The moles of carbon dioxide we just calculated in step 2 to be 0.398 moles, and we need to multiply it by the molar mass of carbon dioxide, which we can quickly work out by getting the molar mass information about carbon and oxygen from the periodic table. And so the molar mass of carbon dioxide will be 1 times the molar mass of carbon plus 2 times the molar mass of oxygen, which gives us 44.09 grams per mole. We substitute that value into this equation, giving 0.398 moles times 44.09 grams per mole, and we get 17.5 grams of carbon dioxide produced. So we started with our 5.78 grams of butane. In step 1, we calculated the moles of butane and found that to be 0.0994 moles. In step 2, we used the ratio of the stoichiometric coefficient to calculate the moles of carbon dioxide, being 0.398 moles. And finally, in step 3, we converted the moles of carbon dioxide to mass of carbon dioxide by using the rearranged molar mass equation, and we found that to be 17.5 grams of carbon dioxide. So this diagram here gives you a very good guide as to solving these stoichiometric calculations involving balanced chemical equations. If we are given the mass of one substance A and are asked to find the mass of another substance B, then we need to convert the mass of A into moles of A, step 1. Then we convert the moles of substance A to the moles of substance B using the ratio of the stoichiometric coefficients, that's step 2. And then in step 3, we calculate the mass of substance B using the rearranged molar mass equation of mass equals moles times molar mass.